Next, we're going to talk about permutations. Suppose you have 8 books that you're placing on the shelf from left to right. How many different ways can the 8 books be arranged on the shelf? So here I have your 8 books in the 8 positions. Now, the first thing you need to do is decide which book you want to put on the very first position. And since you have 8 books to choose from, you have 8 choices right here. But then on the next choice, so you put one of the books up on the shelf, okay? But the next choice, you don't have 8 choices anymore. How many books do you have left in your hands that you're having to decide who goes second? Well, you only have 7 books left. And then after you place one of those books, then how many choices do you have left after that? Well, you only have 6 books left in your hands. Once you place one of those books up, then you only have 5 books left, 4, 3, 2, 1, all the way down the line. Using the multiplication principle, if I multiply each one of these choice numbers, I can find out how many different ways the 8 books can be arranged. So I'm going to get my calculator out to do that. So I've got 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that comes out to be 40,320. So there's 40,320 ways you could put the books on the shelf. This is an example of a permutation. A permutation is an ordered arrangement of items that occur when no item is used more than once. Notice every book was only used once on the shelf. So that's number 1. And the other item is the order of arrangement matters. So in this case, we cared about what order the books were in the shelf. So because order mattered, this is a permutation. So here's a couple more examples of permutation. 5 performers are to present their comedy acts on a weekend evening at a comedy club. How many different ways are there to schedule their appearance? Okay, so first of all, there's 5 performers and they're only going to perform once. So that qualifies as the first condition needed for a permutation. And how many different ways are they to schedule? So it matters who goes up first. Usually the first couple ones are a good prime for the audience for the later ones. So you kind of want to be in a later performance if you could do that. So those are the 2 conditions that are met for being a permutation. So we're going to put the 5 different positions down. This is first, this one performs second, this one's going to perform third, all the way down to 5th. Now, there's 5 performers backstage. How many different ways can the first performer come out? Well, there's 5 different people they could choose from. Now, once that first performer is gone on stage, there's only 4 people backstage that they can pick from. And then 3, and then 2, and then 1. When I multiply this out, I get 5 times 4 times 3 times 2 times 1, and that's going to get me 120 different ways that the performers could perform on that evening. Next, you have a combination lock with a 3-digit code to unlock a combination. There are 10 possible digits, and the digits cannot repeat. How many different possible codes are there? We have 3 digits. There are 10 possible digits, so for the first one I can have 10 possible digits. But because the digit cannot repeat, that satisfies condition 1 from my permutation. And does the order matter in a combination lock? Well, sure it does. So just the fact that it's a combination lock means that this truly is a permutation. So we have 10 different digits for the first spot. Then because you've used 1 for this first spot, you only have 9 left. And then after that, you only have 8 left because you can't repeat any of them. So 9 times 8 is 72, times 10 is 720 different combinations that you can choose without repeating any of the digits. Now, typing all these multiplications in your calculator can get a little bit cumbersome. Notice in our book example we computed 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's a lot of numbers. So to write this faster, we can write 8 multiplied by every single digit down to 1 as 8 with an explanation point, and we call this 8 factorial. That's how it's pronounced. So 1 factorial is equal to, well, just 1. 2 factorial is 2 times 1, which is just 2. 3 factorial means 3 times 2 times 1. 4 factorial means 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which turns out to be 120. And then 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 720. So this is a lot to type in the calculator. It's a lot to write out. So most calculators have a factorial button. So I want you to take out your particular calculator at home and see if you can't find an explanation point on your calculator. Sometimes it'll be on the up in the like green area, but I don't see it on mine. So I'm going to go into probability, and notice right there on number 3 we have an explanation point. Because we're in a probability unit, mine happens to be in a menu. Okay, so if I wanted to type 6 factorial just to check that this truly was 720, I could type 6 and then probability and then go down and choose 3 and hit enter, and truly is 720. So if you could find your factorial button on your calculator, that would be great. The other thing I want to note is 0 factorial. 0 factorial, by definition, let me show you this, my calculator here, is 1. I know that doesn't really make much sense, but we need it to be equal to 1 for other formulas that we're going to be using. So by definition, 0 factorial is always 1. Now in algebraic terms, factorial notation states if n is a positive number and the notation n factorial is the product of all positive integers from n down through 1. So n factorial is n times 1 less than that, n minus 1, times n minus 2, times dot dot dot, times 3, times 2, times 1, all the way down to 1. In a formula that we'll be using very soon, we're going to have to evaluate lots of factorials, and I'm going to show you how to do some of these without the use of a factorial button, especially when you have a factorial in the numerator and a factorial in the denominator. 9 factorial means 9 times 8 times 7 times 6 factorial. The reason I stopped at 6 factorial is because I happened to see that there was a 6 factorial in the numerator and the denominator, and that each one of those is going to divide out, because 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. So the 6 is going to divide with the 6 in the denominator, the 5 is going to divide with the 5 in the denominator, and the 4's divide out, the 3's divide out, the 1's and the 2's and the 1. So all of those are going to divide out nicely, and all you're left with is 9 times 8 times 7, which is equal to 504. Our next problem has 16 factorial divided by 11 factorial. So I'm going to write 16 factorial as 16 times 15 times 14 times 13 times 12. And then at 11 factorial, I'm not going to keep going any further because I can see that there's 11 factorial in the denominator and 11 factorial in the numerator, and that's going to divide out nicely. So then I get my calculator out and type 16 times 15 times 14 times 13 times 12. And that gets me 524,160. Okay, and this is helpful because sometimes your calculator isn't able to do like the factorials, the numbers get too big and they're not able to compute it. For the next problem, we have 100 factorial divided by 99 factorial. 100 factorial seems like it's really difficult because it's going to be 100 times all of the digits all the way down to 1, but because there's a 99 in factorial in the denominator, the 99s just divide out and you're left with 100. So this one was actually really easy. But if I tried to get out a calculator and actually type it in, I get 100 factorial divided by 99 factorial, and it says error. It's not because there isn't an answer, it's because the computer in the calculator is trying to actually multiply 100 times 99 times 98 times 97, and there's not enough screen or computing power for it to actually do that. So it's important to know how to do some of these by yourself, because sometimes the calculator isn't going to help you when the numbers get too big.